Hi and welcome everybody to our question and answer live session on chromatography and purification. I'm Csaba Szabados, the development chemist for chromatography here at Büchi Labortechnik, and I'm here with Bart Denule, our chromatography expert, who is ready to answer all of your questions. We are very excited to be here and to start our discussion on purification soon. We have already collected certain discussion points and different topics we want to discuss about, and we also answer questions that you provide us. Before we start, I would like to go through certain items that you know how to participate in today's session. Here you can see a screenshot of an attendee interface. You should see the control panel in the upper right corner of your screen. You will have the opportunity to submit further questions by typing the questions into the control panel's questions section. You may send your questions at any time and we will collect and include them. We're glad that you joined this session, and we will start with a short introduction from Bart about the discussion topics we will be covering today.
Hi everybody, good afternoon or whatever time it is for you online here. In the invitation, you have seen that there were a few topics indicated already, so we will handle these first and then bring in the questions that you send us already or during this session. So the first topic that we briefly want to touch is about light scattering detection. So how can ELSD help you to detect more compounds in your sample? Let's have a look to what customers typically use in their lab. So I believe that everybody is familiar with the UV detector. So the UV detector is really the workhorse in many labs for different reasons. It's a very easy to use detector. It's compatible with gradients, so you can change the composition of your solvents during a run. And also, especially if you link it to purification, it is a flow-through detector, which means that at the outlet of the detector, you still have all your sample available for further work. However, if we have a closer look to the detector, like with anything in the world, there are also the backside of the medal, there are a few drawbacks linked to that detector as well. The first one is, and that's an important one, that the UV detector is only generating a signal when the compound you want to detect is absorbing light. If that compound does not absorb light, it will not be visible and you will see no peak. Now, let's say the most frequent compounds with very poor signal or no signal at all are the compounds without chromophoric groups. Another drawback as well is that if you see a peak, that it is difficult to judge if that compound is present in the sample as a high amount or just as a little bit, because the response is very dependent on the extinction coefficient of the compound. And that extinction coefficient is very different for different types of compounds, which makes that the peak height might not be the same for all the compounds present in your sample. That means, as a conclusion, if people use a UV detector, it might mean that you're never sure that there is really nothing present if you don't see a peak. It might be a compound that it's not absorbing light and not visible in your chromatogram. So as an addition or as a backup or as a different technique to overcome these negative points, the light scattering detector has been introduced. It became more and more popular also in the purification market segment over the last, I would say, 8-9 years maybe. So let's have a look first to the principle of that detector. Well, it's a very simple principle, actually. It's a three-step process. The first is what we call nebulization. That's where the liquid coming from the column is mixed with the gas, an inert gas, nitrogen, or in some cases, simply compressed air can be used to achieve that. So in that nebulizer, we are forming an aerosol with small droplets of mobile phase. And if a compound dilutes from the column, that droplet will contain a little bit of sample as well. The next phase right behind that nebulizer is an evaporation step, where the mobile phase is evaporated throughout that heated tube, if you want. So at the end of that tube, only the non-volatile particles remain, and all the solvent is evaporated by them. The third part is the important step then, is where these non-volatile particles enter the real detector block. In that detector block, a light beam is generated, and that can be a lamp or a laser or whatever. So these solid particles hit that light beam and scatter light. And the scattered light is then related to the amount of compound that is present in the sample. So how can we now benefit from this light scattering detector? Well, let's look first a bit to let's say the negative points of this detector, if you want, or the limitations better. First of all, and that's an important one to realize, your compound should not evaporate together with your mobile phase. If that happens, you will see no peak, of course. So volatility of the compound is important. The second one to realize, and we might come back on that later eventually, is that the light scattering detector is a destructive detector, in contrast with the UV. That means that what comes out of the detector is not useful for further work anymore. So that's an important one to realize when we start talking about using light scattering for purification purposes. But on the other side, on the benefit and the feature side, we have a lot of positives. And the first one is really, let's say, in contrast with what happens on a UV detector. This light scattering detector detects everything. Everything, because the detection depends on the size of the remaining of the non-volatile droplet or particle, if you want, and not what is in that particle. So if you have a pharmaceutical product in there, or a sugar, or a polymer, or whatever, if the particle size is the same, the signal will be the same. So it sees everything, and it is independent on extinction coefficients. It's also a mass detector, means that if you see peaks of more or less the same height, that also in reality, the compounds will be present in that same ratio. So it's not so that you can be completely off due to the extinction coefficient like on the UV detector. What you see in the chromatogram is reality. And another one, as we evaporate the sample, it does not really matter that you have to take care about the type of solvent you're using. The only parameter you have to take care of, as I mentioned, is that it needs to be volatile. The mobile phase needs to evaporate. But besides that, you can use anything that you want to use or that you need to use for your application. So you don't need to worry about UV cutoff of the solvent. There is no solvent left, so it does not play. In the chromatogram here on the bottom, you see an example. So the green signal that you see is the light scattering signal. So if you look to that first peak here, that means there is no UV trace at all. There is no colored blue or purple trace here. If you would only use UV, you would never see that compound and as a consequence, never collect it. So with UV, if you want to be sure you have everything, you have to collect all. If you use a combination of UV and light scattering, or light scattering on its own, you can only collect the peaks, because there you have the big confidence that you will have collected everything that is present in the sample.
Very nice. So here we have the first question already. It's from Mian from Germany. And the question is the ELSD detection suitable for quantitative measurements? And if yes, what is the theory behind the detection technique?
Well, let's say, as I mentioned, the detector as such is giving a real picture of what is present in the sample, but unfortunately, the response factor for every compound is not 100% exactly the same. So it is not possible to, without calibration, to quantify compounds. So if you really want to quantify compounds, you have to make a calibration curve with standards, which might be a bit cumbersome and time consuming. But by looking at the profile as such, you will be able to judge if these compounds are present in big quantities or small quantities. So real quantification is not possible, but you have an idea about the reality in the sample.
We have a second question on the ELSD topic, which is from Iceland, from Maunian. It says ELSD is a disruptive detector. This is right. My question is about interfacing between preparative chromatography and ELSD.
That's an important question because, well, in flash chromatography or in purification, we are really concerned about our sample. We are looking to purify the sample. We are looking to collect as much of our purified compound as possible. So we don't want to lose sample. Now, as I mentioned, the ELSD is a destructive detector. So somehow everything that is sent to that detector will not be available anymore. So it is really key to make sure that the amount of sample that transfers into that ELSD is as small as possible. Now at Büchi, we are using a special technique which makes that whatever the flow is in the system, so big columns, small columns, doesn't matter, the split towards the ELSD is always 30 microliter per minute. So if you work at 20 ml per minute or at 200 ml per minute, it's always 30 microliter, which is the smallest amount that you can find on the market these days. So we are pretty confident that the amount of sample that gets lost by using a light scattering detector is very, very minimal.
The next question is from the Philippines.
I think that before we go to the next question, that we try to cover the other topics that we announced in the invitation. So it's a bit about sample loading. How do we introduce the sample in a flash system? Well, there are two ways to do that. Two main ways to do that. The first one is easy one. Is if you have a liquid, is just inject the liquid directly onto the cartridge that you use on the system. Now, you have to be a bit careful there because it might happen, and we often hear that people don't really take that into account, that there might be solubility problems. Somebody is preparing a sample and he gets the sample in a solvent at the end of his step and he wants to introduce. Now, in many cases, that solvent in the sample is not the same as what will be used as mobile phase to do the separation. And what can happen if you don't take care, or if you don't know even what is in your sample, that compounds precipitate when you start your run because they are not soluble in your starting conditions. So to avoid this, I would say the best way is to go for solid loading. How does that work? Well, the liquid sample that you have available is mixed with a solid support if you want, thoroughly mixed, and the remaining solvent, or the solvent that you introduced, is evaporated, and the dry powder with the sample on it, coated then, is transferred in a tube and put in front of the column. So the mobile phase elutes what is in that solid loader onto your column, and it will only dissolve what is soluble in the composition of your solvents onto the column for further separation. So to be sure, or to be confident, or to avoid any problem, I would highly recommend to use the solid loading. There is another thing that comes in place there, is that by doing, or by using the solid loader, that you also improve the chromatography. You have smaller bands. That means if you have smaller bands, that you will have better separation. So here you see a few examples of how a solid loader can look like. Here on the left is, let's say, a reusable system, which can be, where the hardware can be reused. We just change the inside with the sample, or you have either packed cartridges already, which allow here with an empty space on top to load the sample on, or a cartridge type empty tube, which allows you to put your support and sample in it and directly put that on the flash chromatography system. And the third topic that was mentioned there was flash versus gravity. We can probably discuss more than an hour on that topic only. Open columns are still often used, but there are quite some, let's say, drawbacks or negative points related to it. It's a long elution time. You don't have much control on the flow because it's just going by gravity. You probably, or in many cases, you need a lot of solvent to elute. You have very limited gradient capabilities to influence your separation. Usually when people use open columns, there is no detector, there is no fraction collector. So a lot of negative points. When looking at a cartridge type, well, I think we can flip it over completely and then just go over the same points, but then on a positive side. We are working with the pump, so we have a controlled flow, we have much faster analysis, so we are talking about minutes instead of hours with the big open columns. There is reduced solvent consumption, there is a built-in detector, there is a fraction collector, etc. So a lot of positive points compared to the open column.
Ready for the next question, Bart?
I am.
Okay, so this is from the Philippines. It's about sample loading.
Okay.
The question is, what is the range of amount of sample loading in the prep HPLC column? What degree of purity is required for prep HPLC?
Well, okay, so loading on a column, also there we can have many discussions, and I would say giving real exact numbers is probably difficult, but there is a very easy rule of thumb for prep columns. We are not talking about cartridges, but about prep columns here. If you have a 150 millimeter column, a 15 centimeter long column, the minimum amount that you're allowed to load is the square of the diameter. So it means that if you have a 10 millimeter column, the minimum amount is 100 milligram. The maximum amount is about 10 times more. That is for a silica packing material. If we talk about the bonded phase, the C18 and C4 or whatever, this is much lower, so it is 10 times lower. So it means the minimum is the square of the diameter divided by 10, and the maximum then is the square of the diameter. Okay, so that's a very easy rule of thumb to memorize. If you would have a different length, it's just the ratio between the lengths. So a 25 centimeter column is 1.7 times the 15 centimeter column. Okay.
Good. So the next question is from the US, from Wade. He is asking, hand-packed columns versus cartridges. What are pros and cons? Pricing on cartridges appears to be very overpriced. What is your input?
Well, I think the pros and cons we already discussed with the introduction there, so I don't think we have to repeat that. I want to give a comment on the price. I would strongly advise to really compare apples with apples. And I know from experience that this is not always the case. It is true that if you want to pack your own column, that buying silica is pretty cheap. So people might think that the price of an open column is much lower than for a pre-packed cartridge. But you have to consider a few other things. You have to fill the column yourself. You have to empty the column after you used it. You have to rinse the column. You're using time, you're using people, you're using solvents that you need to pay, and so on. So it's not just comparing the real cost of the material. There is more into it than that only. Also, as I mentioned, with the open column, you have no detector, you have no fraction collector. So typically people collect everything. Means that they have a lot of work afterwards to verify in all the fractions they collected to see what exactly is present and where their compound of interest is. If you use the cartridges, as I mentioned, you can only collect the peaks. You don't have to worry about all the rest, so you have much less fractions and much less work afterwards. So I think if you calculate that all in, I'm not so convinced that the cartridges are more expensive than the open columns.
So thank you, Bartosz from Poland, for your next question. It's the following. So how do you reduce the formation of channels in self-packed columns?
That's an interesting one. It's somehow, if you pack columns, it becomes more difficult with the size of the column. Small columns are easy to pack with the very minimal risk of having channels. The bigger the column gets, the more complicated it gets. And without vibration, it will never work. Now, if that is too complicated or too cumbersome, I would say the best way to avoid channels is to fill your column with a slurry instead of dry powder. It's a bit more work, but you will have a much better quality of the packing bed. So for bigger size of columns, I would recommend to use a slurry instead of the dry powder.
Next question is from the UK, Pavan. Which is more efficient, liquid packing or solid packing?
Well, I briefly mentioned already that if you use a liquid or a slurry better, so you are not able to dissolve, you just make a slurry to pack, that you typically will get much better results and much better efficiencies in your column than filling it as a dry powder. What I would say is that if you look to the different types of columns which are available on the market, as I mentioned, the open columns, there you have a choice. You do it yourself, you fill it with the dry powder, or you go for the slurry. If we look to the cartridges, these cartridges are typically dry packed. I'm not aware of any manufacturer in the world who is packing flash cartridges in a slurry. it's much more work to do it. It's more expensive, and we already had the comment about the price, so we have to make sure that we don't even further increase the price of the cartridges. So for flash cartridges, I would say it's always dry packed. If we go to HPLC columns, it's the inverse. It's always slurry packed, because the packing there really needs to be optimal, because typically we work with smaller particles, so we have to make sure about the quality of these columns.
Jérôme from the Netherlands is asking, what is the best solvent to store flash or prep columns for further use? Silica, C18, diols, etc.
That's a tricky one, and that's a question we often get. It's about storing cartridges. I would say if we talk about silica cartridges, about normal phase, we recommend that this is single use. Now, people might say, yeah, but you're a manufacturer, you're saying that because we would buy more. Yes, this might be a reason maybe, but that's not the main reason. There are technical reasons behind there as well. Because silica is such a polar material and so sensitive to, let's say, to traces of water that can enter through the solvent, through the sample, whatever. The water sticks to the silica and changes the selectivity of your material. Means that you get different separations as you keep on using that cartridge. So that's why we don't really recommend to often or frequently reuse the normal phase cartridges. When we talk about the reversed phase cartridges, there it's a different story. Or maybe before I go there, if you want to store the normal phase, the best way is to use alcohol, isopropanol. So make sure that the column is flushed with isopropanol. Make sure that you close the inlet and the outlet so that the packing bed is not drying out over time, because once that happens, it will be very, very difficult to get the cartridge back into its original performance. So back to the bonded phases there. Of course, these are much more expensive, and there people expect that they might reuse the cartridges. And it is also possible to do that. But also there, you have to make sure that you keep the cartridges under water and solvent mixture. So I would say about 30% water and 70% organic, and I would go either for acetonitrile or ethanol to do that. The reason why the organic needs to be there is to prevent that bacteria grow inside the column. So even with pure water, so not only the bacteria, but also many materials do not resist 100% water. So the phase, the C18, will get, not physically, but will get damaged. It will cause a phase collapse, which will mean that your retention of your cartridge will be completely different as before. So never use 100% water to store. Make sure that there is organic solvent present.
Ricardo from Mexico is asking how many times you can use each column and how to stabilize them. Oh no, we had, yeah, 1 second.
Yeah.
Yeah, no, it's right. It's right. It's just a very similar question. How to stabilize properly the column before I inject the sample. Thanks in advance.
Well, as I mentioned again, the normal phase we don't recommend to use, or at least not too often, maybe 2-3 times if you're lucky. But I always say, if I get the question, how often can we use a cartridge, even a bonded phase cartridge? If you don't take care, once, and your column or cartridge is ruined and you can throw it away. So it really depends on different factors. It depends on the sample. It depends on the solvents that went over the cartridge. If you reuse the cartridge, it depends on how it has been stored. So it's very difficult to predict or to say in advance how often that cartridge will be able to be reused. I once had the case where it was really a very dirty extract. It was an extract from truck tires, was completely black. There was no way to reuse that cartridge afterwards. It was over and out, one shot over. So it really depends. A question which is very hard to answer. How to stabilize though? We already mentioned a few times that the cartridges are supplied with the dry powder inside. So before starting any purification on that, the packing bed needs to be wetted. Whether that is normal phase or reversed phase, you have to bring in solvent so the cartridge is ready to do the separation. And typically, we do that equilibration, as we call it, with the standard conditions of the separation you want to do. So, for example, a normal phase typically will be flushed with hexane ethyl acetate mixture to make it ready and then be able to start the purification of the sample.
I'm getting another very similar question. This is from Nikolai from Russia. How do you reuse Büchi silica gel-filled cartridges after one separation? What is the best condition to recover the cartridge?
Yeah. Well, I would say it's not only applying to Büchi, but to all cartridges which are used. Again, if you plan to reuse, I think you should make sure that at the end of the separation you're doing, that you flush the cartridge with what we call a high concentration of strong solvent to elute eventually any compounds that would stick to the column. Or better, we discussed the solid loading already, and that's another advantage that I didn't mention, but that comes in very handy for this question here. If you use the solid loader, you only elute what is soluble in the mobile phase. So anything which is present in the sample, which will not dissolve, will stick on your solid loader and will never make it into your column. If you do a liquid injection, you inject all these compounds on your column and you will have a very hard time to get them off again. So even for this, I would say the solid loader can act as a pre-column and can save and protect your separation column if you want. So again, another reason to prefer solid loading over liquid injection.
It's a good idea to use a pre-column as the solid loader. So Ken from the US is asking, in your opinion, what column stationary phases are essential for purification of a wide range of small molecules in R&D labs?
Okay. There are different functionalities available in the market, and that's not just because we want our manufacturers or suppliers want to sell more. There are reasons for that. And what I would recommend is that, first of all, you look at polarity/solubility of your compounds, because that's determining a bit what you will do afterwards. So if your compounds are soluble in water, for example, the choice will be very easy. You will have to go for a column material where it's easy to work with water, which will be, in many cases, a reverse phase material, C18 or similar. Again, because the water will completely change the properties of your normal phase column if you would decide to go for silica, and that's not what we want. So polarity, solubility is really an important factor in there. But to be able to handle everything, I would say a silica material should be available in the lab. C18 should be available. And depending on the application you have, but that's already a bit more specific then, you can go for that C18AQ as we call it. So if you really have very polar compounds, you need a lot of water to give them retention. So you need special C18 material to avoid that phase collapse that I mentioned before. Or people looking at peptides, proteins, for example, will need a material with bigger pore sizes. So there it would be good that they have in the lab a C18 wide pore material. But with silica and C18, I would say you can cover a very big portion of all the applications already.
We're getting a question in from Portugal, which is, when do I use reverse chromatography?
It links a bit into the previous question, I would say. It's all back to that solubility thing again of the compounds. Huh? If your compounds are only soluble in organic solvents like hexane or ethyl acetate or so, then it will be silica. So again, for reversed phase, I would say if you have water-soluble compounds or somehow water or alcoholic solvents come in place during your preparation, it will probably be best to go for the reversed phase option.
Venkata from India is asking, which default method do you recommend to separate very close impurities in reversed phase columns?
Ooh, that's a difficult one. If I hear very close compounds, first thing I would do is, I realize it's not possible to know that in all cases, but I would go back to the compound itself. How similar or how different are these compounds? What I mean is, if the difference between these compounds is in the polar functions, using a reversed column will not help at all. Because a reversed phase column works on hydrophobic interaction, and if the hydrophobic part of the molecule is not different, you will never be able to separate them. So I would say it comes down to knowing the chemistry a little bit to decide what exactly needs to be done. So it might be needed to drastically change the stationary phase. If you're working already on a reversed phase column and the difference is in the polarity of the molecule, then you will have to switch to another polarity, to an amino, to a silica, or whatever. If it is in the hydrophobic part, you can try with changing the solvent, maybe optimizing the gradient, maybe changing the particle size, go to smaller particles, which allow you to get better separations. So it's a difficult one. I would say there is no general rule. My recommendation would be look at the chemistry first of the compounds, so you can decide what route to take.
The next question is, can acetone be used as an element in both reversed and normal phase chromatography using silica as a phase matrix?
Yes, it is possible. However, there is a bit of a consideration to make here, because for acetone has a very high UV cutoff. I think it's around 300 nanometer or even a bit higher. Means that if you use the traditional UV detector, you will not see your compounds because everything will be masked by the absorption of the acetone. So from that perspective, I would say if you only have UV detection, acetone would be a no-go because you will not see anything. But fortunately, as we mentioned in the introduction, we have the light scattering detector, where the solvent that we use doesn't really matter because it's evaporated. So by using the ELSD detector, the acetone is evaporated, it's gone, and you will have no problem to see the compounds. So with the proper detection technique, I would say, yes, acetone is possible to use.
Which is the best advanced chromatographic technique to monitor a chemical reaction?
We are talking about advanced technique here.
Mm-hmm.
First thing I would say is, from experience, I would say the vast majority of users are using TLC to monitor what they are doing, because I would say the main reasons: it's cheap, it's fast, so they very quickly get an idea of what is happening in their reaction. If people really want to use an advanced technique, yet that will be analytical HPLC or even HPLC-MS, but that really starts complicating things. You need skilled people to use these instruments, and in many cases the organic chemists or the people doing the synthesis are often not skilled chromatographists, so that might be a bit problematic to handle the units, to make an interpretation of the results and so on. And for sure, it will be much more expensive. So it depends on what the customer really wants, but again, I think most people are using TLC, which is not really advanced, but very cheap and very fast.
Dinkar, thank you for your question. The next question is from India again. Towards getting pure metabolites from plant extracts, how can you choose between normal and reversed phase chromatography?
Okay, plant extracts, exciting, because usually these are very complicated samples. So I would say it depends again on the chemistry. It's all about the identity of the compounds and how the extract is done. Are you using water alcohol or mixtures of both as an extraction solvent, or do you use organic solvents like hexane or similar solvents to do your extraction? Again, if that is, imagine ethanol water is used, well, again, for the reasons I already mentioned before, I think reversed phase will be the choice to do. The normal phase will be in the cases where where organic solvents are used. So it depends on what the customer is looking for, what the plant is, how he needs to extract the compounds of his interest to decide. So again, here it is not possible to predict up front what would be the best. So I would say having both available is a bonus in case of plant extracts, I think.
Mm-hmm. Thank you, Victor from Brazil, for your question. What are the main challenges and methods of fractionation and purification of plant extracts in the industrial field and the lab scale?
Well, I would say that links a bit together with the previous question. Again, it's about the extract and the complexity. Because here with plant extracts, we are not talking about just a few compounds, 5, 6, 7 compounds, but it is not, let's say, it easily goes up to hundreds, 100, 200, 300 compounds in an extract. So I would say the challenge will be to separate all these compounds. And typically we see there that there is not just one purification step, there are multiple purification steps. And these might not always be the same technique. So, for example, if you want to get rid of fat that might be present in your extract, it probably will be a cooling step, a freezing step to remove the fat, so the fats will crystallize and be able to get it out of the rest of the matrix. Or there will be a step to remove chlorophylls with the distillation or an active coal filtration. So it really depends again on what the customer wants and needs finally, and what is present because or due to the extract he is doing. And again, for us, that's a difficult one. So it's not possible to generalize, but that's again a case-to-case study. Let's say what comes out of the extract and how do we need to proceed to get everything separated. And here it comes very handy, and that's something that we have in our portfolio as well. We often see when it comes to plant extracts that people do pre-purification on the chromatography side then with flash. So if you want some type of a group separation, and with one of the groups that they collected, then they go to, on the same system, they go to the prep site and do a more detailed separation of that pre-purified fraction with the prep column on the system. So that's something we often see happening, and that's why I would say it would be a plus to have such an instrument available if you are doing plant extract separations or purifications.
I agree. And I think we hit quite a spot here. We getting plant extract questions here. Okay. The next one is from the Philippines. What is the best chromatography technique for removing organic acids in plant extracts while recovering all other bioactive compounds? I like that one.
Well, usually the ones you like are the most difficult to answer.
Of course.
Well, organic acids don't show a lot of retention on a reversed phase column. So my first guess or attempt would be to run that sample over a reversed phase material, and the organic acids, which do not retain well on a reversed phase material, will elute very early in the chromatogram, and most probably will already be eliminated from the rest of the sample. If that would not work, we have to have a closer look exactly what else, because if you say all the other bioactive compounds, that's difficult. So we need to know exactly what that means for that specific customer to be able to eventually give more detailed advice if in case the initial reverse phase separation would not work.
Mm-hmm. Is it possible to get a pure compound from a crude extract?
That's exactly why we use chromatography for. If that would not be possible, chromatography would not be a good purification technique, I think. So yes, the answer is yes, it is possible. But again, it depends on what you have in your extract, and again, plants are very complex samples. So most probably pre-purifications will be needed. Removal of compound groups which only make the chromatography difficult, like already mentioned, chlorophylls which might be present, fat which might be extracted. So that has to be removed first before going to the chromatography column. Otherwise, it will really become problematic.
Is there a standardized protocol for purifying bioactives from plants, like tannins, flavonoids and phenols, and so on?
I think I have to come back again on what I said earlier. Plant extracts are very complex samples. Also, we know that the plant itself is various as well. So means that the sample or the extract you get is in many cases very different. So talking about a standardized method is very difficult in this case as well, because we cannot really talk about standard samples. So the variation on the sample itself is so big that it's difficult to say, hey, this is the method to use for anything you have as a plant extract. So that doesn't really work. But if I look again to the compounds you mentioned there, the tannins, phenols, and so on, these are polar compounds. Polar compounds probably means that the extract will be done with alcohol, ethanol probably. So from that perspective, I would say that the reversed phase would be the first try to separate these groups. And again, there the flash and prep combination can really help again to do first a group separation, a rough separation, and from there go to a more detailed separation on the prep side of the instrument.
Mm-hmm. I agree. So we will have time for approximately 2 more questions before we run out of time. The first one is Carl from the US. What advice can you give to a customer wanting to scale a flash chromatography step to larger scale?
It depends what the definition is of larger scale. What I mean with that is that on a flash instrument, I would say it's already possible to scale up. For example, on our instruments, you can start working or evaluating a separation on a small cartridge, as small as 4 gram silica. And once you optimized your separation, you can go to bigger sizes, up to 3 kilo of silica already, which allows you to separate multi-gram samples already on the same instrument. The only thing you have to take care of is, okay, if you work with column volumes and set up your method with column volumes, it doesn't matter what the size of your cartridge is. 5 column volumes is 5 column volumes. Whether that column volume is then 10 ml or 1.5 liter, it's 5 column volumes. So you can literally scale up from 4 gram to 3 kilo on the instrument itself. So I don't know if this is already large scale for this specific customer, or if he's talking about production scale then, which is much bigger than 3 kilo, then it's a bit a different story. So there we have to sit down together and make a few calculations, I think.
So we'll proceed to the last question. How to estimate scale-up production for 1 fraction of the technique applied from small-scale flash chromatography?
I would say that that's more or less the same question as the previous one. So again, we have the scale up on the instrument. There exist formulas, but okay, as I have not a lot available here to show things, it's probably not the right forum here to do that. But there exist formulas which allow you to calculate what loading, what flows you need for bigger scale columns. If you start from a given, let's say we do today a purification on 100 gram or a 20 millimeter column. I want to go to a 1 meter diameter column. well, we have formulas available which allow to make the calculations about flow and loading to allow you to predict what needs to be done. But again, this is probably something that needs to happen then in a face-to-face discussion with the customer.
Thank you. So we received so many questions that unfortunately we cannot cover all of them today. We collect all the questions and you will get the answers of all of them through several channels of ours. For this reason, I invite you to follow us on Bart's blog or our LinkedIn profile to be updated on the chromatography topics of interest and much more. Any further questions you have, you can send into marketing@büchi.com or interact with those social media channels. Once you leave the session, you will receive a survey on the presentation, and we would appreciate if you give our feedback. You will also receive a follow-up email within next 2 days with a link to view the recording of this session. On behalf of Büchi Labortechnik and our presenter, thank you very much for joining us and have a pleasant day.
Bye.
Bye.